My name is Al Gashevsky, and I'm chair of the Hans Liebe Fellow Search Committee. The U.S. National Committee, USNC, of the Union of Radio Scientists International, with the generous support of the Liebe family, has established the Hans Liebe Lectureship in Microwave and Optical Spectroscopy as applied to radio science, remote sensing, and telecommunications. This lectureship provides travel support and an honorarium for a distinguished member of the radio science community to deliver a lecture on the professional topic of their interest at each of the annual USNC-URSI radio science meetings. As most of us are aware, Dr. Hans Liebe was the developer of the MPM-93 model for atmospheric microwave absorption and refraction. This model, developed through Hans' meticulous measurements in the 1980s and early 1990s, is a standard that enables much of our contemporary propagation work in remote sensing, radio science, and telecommunications. And for those of us who knew Hans, he was also a great friend to the radio community. On behalf of the USNC-URSI, I would like to express our gratitude to Mrs. Liebe for her support of this lectureship in memory of Hans. Mrs. Liebe can't be with us today, but send her kindest regards. Our 9th Hans Liebe Fellow is Professor Mikhail Tretyakov of the Institute of Applied Physics, Russian Academy of Sciences in Nizhny Novgorod, Russia. Professor Tretyakov graduated from Gorky State University in 1980 with his MS on analysis of subdoppler microwave spectrometer based on coherent spontaneous radiation of molecules. This was recognized to be the best student scientific work in the USSR in 1980. He received the PhD degree in physics and mathematics in 1995 for his thesis on development of methods of microwave spectroscopy in terahertz frequency range. His full doctor degree was received in 2017 for the work High Accuracy Resonator Spectroscopy of Atmospheric Gases at Millimeter and Submillimeter Waves. From 1980 to present, he has been with the Institute of Applied Physics, Russian Academy of Sciences, where he is currently head of the Laboratory of Microwave Spectroscopy and a member of the Scientific Council of the Institute. His interests are in high-resolution molecular spectra experimental studies in millimeter and submillimeter wave range and development of new microwave techniques and methods. Liebe Fellows are provided an honorarium and invited to present a talk on the topic of their choosing. While international travel restrictions have made it impossible for Professor Tretyakov to be present with us today, we are honored that he is available online and available to make his presentation to us. And so without further ado, we'll invite Professor Tretyakov to provide his lecture on laboratory spectroscopy of atmospheric gases in the millimeter and submillimeter range. Professor Tretyakov.
Yes, thank you. Before starting the lecture, I would like to thank organizers for a remarkable opportunity to present results obtained in our laboratory over past 20 years. I really regret that I cannot give this lecture in person. Sorry for my imperfect English. I hope my Russian is better, but it's of no use in this audience. So let me start the presentation. As you see from the title, the talk is about laboratory spectroscopy of atmospheric gases. This is the talk outline. In the introduction, I will briefly give history or milestones of the problem. In the first part, we will speak about paradigm of molecular spectroscopy, which will be helpful for better understanding of spectroscopic content of the lecture. In the second half, in the second part, we will discuss our resonator spectrometer, which is very similar to instruments developed by Hans Liebe. In the third part, we will talk about spectra of atmospheric gases and their interpretation, including resonance lines and continuum, We will talk about empirical modeling of the continuum and its physical origin. So the first traceable steps were made by John Tyndale in the second half of the 19th century. Here is his simplest spectroscopic instrument: heater, warm radiating gas, radiation receiver, reference black body. I cite here 3 phrases from his lecture reflecting the level of understanding of the problem at that time. Different gases absorb radiation differently, but their radiative power follow precisely the same order as their absorptive power. Beautiful, isn't it? Half a century later, important steps were reported by Fowle in his review article, and here are 2 pictures from his article. It was already understood that our atmosphere plays a key role in the Earth's radiation balance, and molecular spectral bands were revealed. Here on the left, you can see CO2 band in between 2 water bands. On the right, you can see oxygen band and water bands in the range of incoming solar radiation, and this figure corresponds to the range of the Earth's thermal emission. The same time frame. The first broadband spectra were reported by Hettner, and here you see a spectrum of water vapor. A clear quasi-periodic structure of the water vapor was revealed. 3 decades later, rotational structure of a molecular band was revealed, and line-shaped models were developed, and detailed modeling of atmospheric absorption became possible. Here you can see one of the key papers from that epoch by Van Vleck, and 2 pictures from this paper demonstrating calculated spectrum of rotational lines of water vapor and oxygen, very recognizable pictures for all radio scientists. All these lines are main atmospheric diagnostic lines now. Jump to present days. Sophisticated line-shaped models have been developed. Line parameters can be now calculated ab initio, and these calculations are competitive with precise experimental measurements. It is possible to demonstrate that observed and calculated spectra agree at sub-percent level. Spectroscopic databases collect and update information. Here on the right is the most famous and most well-known HYTRAN database. It contains now more than 11 million lines of 55 atmospheric molecules, including most abundant isotopes. The figure below demonstrates that atmospheric absorption spectrum can be modeled now practically to the noise level, and this modeling is improved by step-by-step upgrades of the database. But all line-shaped models currently used for atmosphere remote sensing employ an ideal gas approach, instantly colliding particles, with a number of semi-empirical corrections to take into account the result of intermolecular interactions. This simplification limits the accuracy of the atmospheric absorption modeling, and this is the problem. Let us see how this problem can be resolved. So we come to the first part of the talk. So what is absorption medium from spectroscopic point of view? It's a real gas, equation of state, Brownian motion, 10 to the 19th power, permanently interacting with each other molecules in cubic centimeter. And the result cannot be rigorously calculated at the current stage. So we need to introduce several approximations. So first of all, we consider the gas rarefied and close to the ideal. So the second term is much smaller than the first term of the equation of state. Moreover, we neglect triple interactions. So the third term is much smaller than the second one. So we deal only with binary interaction, and the task becomes solvable. The interaction potential can be calculated from first principles, and this allows to calculate typical trajectories of relative motions of molecular collisions, energy exchange, and so on. Two most typical cases of collisions are shown here. It's often forgotten that such collisional trajectories are also possible and are not rare. So the collisional interaction led to formation of pair or bimolecular states, including free pairs, which is one-touch collision with a short-lived dipole moment induced during the collision, quasi-bound dimers corresponding to such trajectory of motion, and bound dimers, which are stable molecules with a total internal energy smaller than the intermolecular bond dissociation energy. So we get new absorbers, which are usually unaccounted for by propagation models. The number of these absorbers can be estimated from the second virial coefficient and corresponding equilibrium constants. To distinguish between monomolecular state and bimolecular states, we need one more approximation. Significant distortion of the structure of colliding molecules occurs only at short distances. Within this approximation, the monomolecular state can be considered as practically unperturbed molecule moving in the field of interaction potential, and pair states as double molecules with their own dipole moment interacting with the electromagnetic field. So what is absorption coefficient? To introduce the conception, we need to introduce one more approximation, which is known as local thermodynamical equilibrium, meaning that molecular energies follow Boltzmann distribution. Within this approximation, the absorption coefficient, which is a relative decrease of power passed through the gas normalized by the radiation path length, can be represented as a product of three terms: the number density of molecules which are able to absorb the radiation quantum, the so-called radiation field term, and molecular spectral function. The last term is a Fourier transform from the molecular dipole autocorrelation function. Let's see the simplest example: hypothetical ideal gas of two-level molecules. The dipole moment of the molecule produces a train of harmonic oscillations between two successive collisions. Averaging over the gas gives almost exponentially decaying process. The spectrum of this process is a very well-known bell-shaped function located at the frequency corresponding to frequency of these oscillations and having the width, which is a reversed duration of this train of oscillations. Let's interrupt for a while the theoretical part and let me introduce one of my most favorite spectroscopic pictures, which I found in a paper by Liebe. It demonstrates that classical line-shaped models agree with each other in the vicinity of the line center, but at large detunings from the line center, the difference between different models can reach several orders of magnitude. This is a problem of wings. It has remained unsolved for decades with a very little progress in describing the phenomenon. Artificial cutoff of monomolecular absorption and empirically adjusted pedestal, which is referred to the continuum, are still used in all propagation models. Let's continue with the paradigm. So what is line shape? Within the impact approximation, the train of oscillation breaks instantly. And this gives a Lorentz function if the collisions are relatively often. So we neglect Doppler broadening. So it's Lorentz function. Well, in reality, the collision takes time. And if this function is smooth, then it gives exponential decay of wings. Note that the shape of this function is determined by interaction potential. And the same interaction potential determines such well-known collisional parameters of line as a pressure shifting, pressure broadening, and its speed dependence, line mixing, and other collisional parameters. It was believed that at large detunings from the line center, the behavior of the wind is always sub-Lorentzian, and the super-Lorentzian line shape is not supported by any known physics. We found the missing mechanism. If this function makes an oscillations, if it's not smooth like here, then you have a broad hump at the frequency corresponding to the frequency of these oscillations. And for example, light molecule can make several full turns during a collision. And the width of this hump corresponds to reverse duration of collision. So explicitly calculated monomolecular line shape should be used for the physically based radiation propagation model. Within this approximation, the total absorption can be represented as a sum of spectra corresponding to different molecular states, monomolecular, bimolecular, three molecular, etc., exactly in the same way as you model the mixture of different gases. By analogy with equation of state, the absorption coefficient can be represented as a product of normalized spectra multiplied by the number of corresponding absorbers. So the third term it can be neglected at atmospheric conditions. And the spectra itself are functions on frequency, number density, and temperature. This is how it should be in accordance with physics. For comparison, this is how it's represented in all propagation models. The only measurable is the total absorption. The continuum is derived as a difference between the total and calculated spectrum of resonance lines. In this case, the continuum strongly depends on the line list, on the line shape function, and the line shape parameters. So here we finish theoretical part and turn to experiment. Our laboratory can be called Liebe's followers because our real contribution to atmospheric physics began from development of our cavity spectrometer. We call it resonator spectrometer, which is very similar to spectrometers developed by Liebe. Here is a drawing of his cavity and a citation from his work. Although there are two differences between our instruments, and they will be discussed a little bit later. This is how our spectrometer looks. Its elements are really big and heavy, so we are using hosting crane, lifting the cavity up and down. This is how it looks in operation. Radiation source, waveguides, gas chamber. By principle of operation, it's similar to modern cavity ring down spectrometers. So when you fill the cavity with gas, its quality is changing in proportion to absorption coefficient. So coherent continuous wave radiation from the source comes into cavity, oscillates inside, and returns back to the detector. The quality factor is near 1 million, and it's determined by a reflection coefficient of mirrors, maximum possible reflection coefficient in this wavelength range. When we scan frequency, we make a recording not of a spectral line, but of a shape of eigenmode of the cavity. The width of this mode is in direct proportion to total losses of radiation in the cavity, which consists from losses in gas and losses in resonator. And the absorption coefficient can be calculated using this simplest equation, using broadening of the width of the mode when you fill the cavity with gas. This figure illustrates how we make a recording. Upper trace corresponds to just laboratory air. The lower trace corresponds to non-absorbing gas. And the difference between them corresponds to radiation losses in the gas in the sample. And the measurements are made at eigenmodes of the cavity. So this is the spectrum. Many resonator spectrometers are known, but there are 2 points that make the difference. The first point is we use fast digital phase continuous frequency scanning. So we make a recording of the mode faster than its shape can be distorted by temperature drifts, mechanical shaking, or even 50-60 Hertz mainline pickups. This allows us to achieve an absorption coefficient of about 4 × 10⁻⁹ cm-1, which is about order of magnitude better than in other analogs. The second major feature is the use of differential measurements, or the so-called path length variation method. This allows us to minimize systematic errors related to water adsorption at the cavity elements. So we simultaneously use two cavities. They are almost identical, and the electrical field distribution is almost identical, but the length is different exactly by a factor of 2. Water adsorption changes quality factor, and this is indistinguishable from gas absorption. These two figures illustrate how big could be systematic error if you use only one cavity. The shorter the cavity, the larger error can be. So we use differential method, and we just subtract the effect of adsorption. The water adsorption was known as a main source of systematic errors in such instruments, and we resolved this problem. This is an example of a broadband recording of laboratory atmosphere spectrum. We are very proud of this recording and call it our visiting card, because the recording is unique, and I doubt that any other laboratory can present such a recording. The wavelength change is about order of magnitude. Let me use this recording to compare ability of our instrument with the best known analog spectrometer developed by Hans Liebe and Boulder. Blue American crosses and red Russian circles coincide with each other on the band profile recording. But if you calculate the difference between the observation and the model, you see that the noise level is order of magnitude smaller in our instrument. This figure demonstrates the same data in more detail. On the left, you see the famous set of points obtained by Hans Liebe and used for development of the millimeter wave propagation model in its oxygen part. On the right, our data on the same scale demonstrate that the model can be improved with the higher sensitivity of the instrument. At this point, it's my pleasure to mention our long and fruitful collaboration with Phil Rosenkranz from MIT. We are really grateful to him for his contribution, for his theoretical support of our work. So we come to the third part of the talk. Let's talk about resonance lines. As I mentioned, all these lines are main atmospheric diagnostic lines, and we studied all of them. And I can give a full-time lecture about any of these peaks. But today, let's concentrate on this weak oxygen line, which is known as atmospheric thermometer. Microwave radiometry undertaken with a polar satellite offers the possibility of a global determination of the approximate vertical temperature distribution in the Earth's atmosphere. This possibility was suggested by Mix at the very beginning of our space epoch, and now almost all space missions use radiometers at this frequency. To use this method, one have to answer two questions. What is the shape of the spectral line, and what is the accuracy of the line shape parameters? Let's answer these questions. The first rigorous study of this line was undertaken in Texas University. A publication in Nature demonstrates importance of the study and appreciation of obtained results. The line is very weak, and this weakness is good for thermometry because our atmosphere is almost transparent at the line center frequency. But this weakness considerably complicates the laboratory study of this line. For this study, very special 150 meters gas cell was built, and authors achieved a signals to noise ratio near 100. You can see here experimental points. They found that classical Van Vleck scope shape is not suitable for the line. And I cite, the shape does not exactly describe the line shape of this oxygen absorption line. Instead, they suggested this rather strange modification, see these strange exponents. The next similar study of this line was undertaken in our laboratory in this period. At the beginning, we used just this open Fabry-Perot resonator just standing on the desk. Then we packed it into a big plastic garbage bag. And we achieved similar to American signal to noise ratio near 100. And we found that Van Vleck scope profile fits, and you can see it from residual. But the line center frequency is slightly shifted down relatively measurements at low pressures. At the beginning, we thought that this is just usual collisional pressure shifting effect. But at that time, we started a collaboration with Phil Rosenkranz, and he explained that this is apparent shift due to the collisional coupling effect. This line only looks like a single and isolated, but it's collisionally coupled to the 60 gigahertz band. So to observe the effect, we increased sensitivity of our spectrometer, and now signal to noise ratio is near 500. And indeed, we found that Van Vleck scope profile does not fit to the profile. See this systematic residual. So the profile should be complemented by these two terms. And this profile is known as a Rosenkranz shape. So this study was the first direct measurements of the line collisional coupling parameter and its temperature dependence. For the study, we used such gas chamber on the basis of usual refrigerator. This is the most recent recording of this line at atmospheric pressure. The sensitivity was further increased, and now signal to noise ratio is near 2000. So manifestation of the line mixing now is observed better than the line in first experiments. And you can imagine our amazement when we found that the Rosenkranz shape is not suitable either. You see this systematic deviation of the residual, which is a typical manifestation of the so-called wind effect, which is a speed dependence of molecular collisional cross-section. At that time, the line profile simultaneously taken into account the line mixing, and the wind effect was not known, but it was promptly developed. So we used quadratic approximation of speed dependence. So we were able to describe the line shape. So this is the line shape. It's not an analytic function anymore, but we do not care because we can calculate it digitally. So what is the accuracy of line shape parameters? The second question. And let me answer it on an example of gamma zero parameter of this profile corresponding to collisional width of the line. Now we deal with the problem of difference between accuracy and precision, which is nicely demonstrated in this figure from Wikipedia. Here on the left, you have precision, but don't have accuracy. Here on the right, you have both precision and accuracy. Here are intermediate cases. And the problem is that, that in experiment, you do not know where the center of the target is. So to illustrate that, I plotted here the history of measurements of this line collisional broadening in pure oxygen and in dry air in chronological order. And you see that many points deviate from each other more than stated error bars. And here are our points for pure oxygen and for dry air broadening, and you see that the precision is fine. For the last point, error bar is smaller than the size of the point. But what about accuracy? To answer this question, we use two spectrometers. Both are behind me, and in principle, we can use opportunity of this virtual meeting, and I can show you if someone would like. So we measure the collisional broadening with two instruments. There is an eta spectrometer I'm talking about in this lecture, and so-called spectrometer with radioacoustic detection of absorption. We call it RAD spectrometer. Together, they cover enormous range of pressures, almost 4 orders of magnitude. And you see perfect linearity of collisional parameters from pressure. Statistical accuracy of gamma 0 parameter, which is collisional broadening, is smaller than 0.1%. And the total uncertainty of broadening coefficient is 0.3%, mostly determined by accuracy of our pressure gauge. So for collisional broadening, this is just question of accuracy. But for collisional narrowing, which is gamma 2 parameter, this is question of physics. Where this narrowing come from? Is it wind effect, or maybe it's Dike effect, or maybe it's just instrumental problem? The reviewer of our paper commented that agreeable results leave no doubt about the physics. This is kind of point in this story. Very recent paper just from September 3rd, 2021, presenting fully quantum calculations of pressure broadening of this oxygen line. And here a figure from this paper and some table. The figure demonstrates that results of initial calculations, which are shown by solid lines, almost exactly coincide with our data from 2016. And in the table, you see numerical agreement at room temperature within 0.09%. So we believe that we have both precision and accuracy. A few words about line intensity measurements. Intensity measurements are known as the most difficult task in experimental spectroscopy. And so many factors should be taken into account. That is why even best spectroscopic groups cannot guarantee accuracy of measurements better than a fraction of percents. We present here reproducible results of measurement of intensity of this oxygen line, which deviates within 0.3% from the most accurate today calculations, which are presented in the HyTran database. Note estimated uncertainty by HyTran's experts, which is 10–20%. Well, so let's come to the continuum. So you may know that these lines are standing on a smooth pedestal, which is a continuum in its usual representation as a difference between observation, which is shown by red line, and a calculated spectrum of water monomer, which is dashed blue line, and the micro windows between lines. You see that the continuum exceeds the resonance absorption by order of magnitude. It was known from long ago that the continuum can be modeled by 3 terms, first corresponding to interactions of water molecules with each other, so-called water self-continuum, interaction of water molecules with molecules of dry air, water foreign continuum, and interactions of other from water molecules with each other, so-called dry continuum. I will skip discussing the dry continuum components because it's almost 2 orders of magnitude weaker than wet continuum. But note that it is still measurable with our instrument, and recently we improved its parameters. So we talk about empirical modeling of the continuum now. It was known that in the millimeter wave range, the continuum can be modeled. Both parts of the continuum can be modeled as a temperature-dependent coefficient multiplied by frequency squared. The figure presents all data before the year of 1998, and Phil Rosenkranz used this data. He obtained values of C and N coefficients and obtained these approximations, which are used until now in the millimeter wave propagation model with minor corrections. Let's see development of this story. In the year of 1995, new data were obtained by Katkov et al. It was field trace 1.5 kilometers along the surface. In the year of 2002, new data were obtained by Agnes Boer group in Lille. Then these black points are our data from 2011, and this data complete the laboratory data set. You can see that approximation made by Rosenkranz is fine above room temperature, but below room temperature, it looks like both coefficients should be slightly increased. Let's now see the result of the continuum measurements using radiometric data. Surface to sky trace measuring thermal emission of the atmosphere. Using the same model, in the year of 2009, Turner et al. Demonstrated that the agreement between the model and the observation can be improved if correction is made as shown by these dotted lines. Later, similar measurements were made by Payne et al. In 2011 and by Vance in 2016. And you see very good agreement of their data for foreign continuum, relatively good agreement for self-continuum, but for the self-continuum, the deviation from laboratory data is significant. In this case, increase of one coefficient is accompanied with a decrease of the other one, which is understandable because within the model, the total should remain the same. So what does it all mean? Some people refer to the mystery of the continuum, and this problem was discussed in a big international meeting in Paris in 2015, and it is related in reflected in related publication. And there is no answer yet. So now let's talk about physical origin of the continuum. In the rest of my talk, I will speak only about what is self-continuum. Because the physics is the same, but more data are available for the self-continuum than for the foreign continuum. The problem is discussed almost during 1 century, and all possible reasons are listed here. So unknown lines, unknown monomer lines, this possibility become possible to exclude after global ab initio calculations of what a monomer rotational vibrational spectrum become available. Remarkable work by Oleg Polyansky and his colleagues. Collisionally induced dipole. There are 3 very different estimations illustrated. They all agree that this possibility of physical origin of the continuum is impossible. So this contribution for water vapor at atmospheric conditions is totally negligible. Far-wings. This is the most difficult to estimate. However, some estimations are possible in the so-called quasi-static approximation, when one molecule can be considered in the permanent field of another one. And such estimations were made by Rosenkranz in 1987 and later by Ma et al. In 2008, and they agree, but this contribution should be small. What are dimers? For the first time, the dimers as a possibility as a region of the continuum was suggested by scientists from our city, Sergei Zhivakin and his PhD student, Alla Viktorova. By the way, both were my teachers at the university. The later, so it was 1966, and then this conclusion was theoretically supported by Andrei Vigasin and Chlenova in 1983, and by ab initio calculation by Scribane and Le Forestier in 2007. This slide demonstrates the difficulty of experimental confirmation of the dimeric hypothesis of the continuum. This is kind of conclusion of a big international meeting devoted to molecular complexes in our atmosphere and beyond. I cite from introductional paper from the special issue of molecular physics on this subject. Yes, the water vapor dimer is very likely to be present in our atmosphere, and yes, it is expected to contribute a profound fraction of the radiation budget. Beware of fakes when searching for evidence of complexes, and make sure that monomer contributions are accounted for up to the latest details. There was no reliable contribution about dimeric hypothesis until the year of 2013, in spite of significant efforts of many experimental groups all over the world. Why it was so difficult? To understand that, let's consider in more details the water dimer and its spectrum. From the first glance, the water dimer is very similar to the atomic molecule, but presence of 4 identical protons makes the tremendous difference. First of all, it gives 2 additional axes of rotation. Then it gives 3 low barrier tunneling motions. Then it gives 6 intermolecular vibrational modes, and they are low frequency. They are all populated at room temperature. So you have tremendous amount of molecular states. Because of these complications, the spectrum of water dimer is significantly different from the nice diatomic pattern. However, the so-called E-type transitions, which are shown here by red sticks, somehow they keep memory about the atomic structure of the molecule, and they group together around positions corresponding to the end-over-end rotation of the molecule. So at pressures, when these lines overlap with each other due to collisional broadening, the spectrum demonstrates this quasi-periodic structure, which is very similar to the atomic pattern. The structure disappears at frequencies above 400 gigahertz because of accumulated centrifugal effects, but below it's really visible. This slide demonstrates the result of our trial to observe this quasi-periodic structure. The experimental recording is shown by this yellow-brown color, and it looks like a noise, but it's not noise. The spectrum is reproducible, and so all these peaks can be reproduced, and the spectrum shows correct behavior in temperature and in pressure. And the spectrum is shown here after subtraction of monomer spectrum, which is shown by this dashed blue line. The solid black line is a model, and the maxima exactly corresponds to positions of the end-over-end rotation, which are very well known from cold molecular beam experiments. And this agreement allowed us to state the first unambiguous detection of the dimer in warm water vapor. The result was highly appreciated by international scientific community. This is annual report of Russian Academy of Sciences to our president, and I cite from page 29. In the year of 2012, the most interesting was the registration of resolved rotational spectrum of a water dimer in water vapor at room temperature in the millimeter wave range. What about high frequencies in submillimeter wave range? The figure shows all data which were known about the continuum in submillimeter wave range before our investigation. The dotted brown line corresponds to empirical extrapolation of the millimeter wave data. The dashed blue line is empirical approximation of fine infrared data obtained by Podobedov. MTCKD model, well known when widely used all over the world for the continuum modeling, goes just in between, very diplomatic. And these scattered green points are unpublished data obtained by Bollander and reported by Birch in 1981. So the behavior of the continuum is really uncertain. To study the continuum in this range, which is known as terahertz gap, is not easy task, and very special instrument should be used. It should be broadband and very sensitive because the continuum is weak. We found such instrument near Paris, Soleil synchrotron. So we applied, and the International Selection Committee supported our proposal. So we were able to use synchrotron radiation with a high resolution Fourier transform spectrometer, equipped with a multipass gas cell with a total path length of 150 meters at room temperature. The green trace is a typical experimental spectrum, and the dashed black trace is a calculated water monomer using Hydra. And the continuum is just seen as difference between these two, and we plot it here. Now let's plot it in this figure. And we were happy to see that our data, just like a bridge, they unify millimeter wave data and fine infrared data. And it was nice to see that the good agreement between our data and this unpublished data by Bollander. It is well known that this quadratic behavior of the continuum is not a property of matter, but this is a matter of radiation theory. And to see the property of matter, you have to normalize the continuum spectrum by frequency squared. So we do it with this data, and all this, the same data are plotted here on the right. And now I plot here the water dimer spectral function obtained from sophisticated ab initio calculations by Scriban and Lefrestier. Remarkable agreement, isn't it? So this is independent experimental confirmation that water dimer dominates the continuum in the millimeter and sub-millimeter wave range. So let's return back to this problem. I do not believe in mystery. I think it's the problem of the atmosphere modeling, in particular, modeling of vertical distribution of absorbers. The atmosphere is not ideal gas. It's amazing, but all propagation models still ignore existence of dimers. So we come to conclusions. I will briefly list the yield of our laboratory resonator spectrometer. Regarding resonance lines, the most important from fundamental point of view is experimental confirmation of theoretical shape of broad atmospheric lines. It's also a very important experimental study of the collisional line coupling effect in the spectrum of oxygen. For applications, it's important verification of collisional broadening and shifting parameters of atmospheric diagnostic lines measured at low pressures. And also verification of theoretically calculated intensities of atmospheric lines. Regarding the continuum, we determined the most reliable empirical parameters of the atmospheric continuum. We made broadband recordings and parameterization of water dimer spectra at close to atmospheric conditions, and we present the first experimental proof of the dominant contribution of water dimers to the wet atmospheric continuum in the millimeter wave range. Using the chance, let me advertise the very recent book where all problems discussed in this lecture and many other useful information is collected. The book is available from Cambridge School of Publishing. Also, I would like to thank all people from our laboratory for remarkable results we obtained all together. And then I thank you all for your attention. Thank you very much.
Professor Tretyakov, I want to thank you very much for an outstanding presentation on excellent work that you've been doing. This is really so beautiful to see it all put together in such a fashion. So thank you very much.
Thank you. Thank you.
I'm sure you're going to have people buying your book too.
I hope.
I will. I'd like to open up the lecture for questions if anyone has any for Professor Tretyakov. Or if there are questions from our Zoom audience, please. And maybe I'll start off with a question. I think people need to perhaps digest a little bit. The dimer spectrum around 170 gigahertz, where you showed these small blips in absorption. These little blips in absorption were actually fairly sizable, on the order, if I recall, of 1 or 2/10 of a dB per kilometer.
Yes, let me find this figure. Yes. I cannot do it quickly, but let's just. Yes, they are really weak, but as well as I remember, they correspond to about 1 Kelvin of brightness temperature. So we made an estimation. Oops, it's too far away. Back. Yes, here we go. Yeah, do you see it?
Yes, yes, exactly what I was referring to. These are very sizable peaks, and I could imagine them having an impact on brightness temperature of order of a Kelvin. I could also imagine them being directly measured with a long path transmissometer.
Yes, I hope so. Actually, this solid black line, this is a model, and the model is reported in the paper. Odintsova is the first author, and well, you can use this model.
Yeah, this is very interesting, and again, highly relevant in terms of the impact on our use of these models.
Yeah.
Yeah, any other questions?
So on the measurements from the Salil instrument, they're supposed to be able to hear me. Can you hear me?
You should be able to.
Yes. So if you can advance a few slides on the Salil measurements, you have that big rise at the end. So I think it's 2 slides ahead.
This one?
Keep going. Your measurements.
Our measurements. Okay. This one?
There. Yeah, that feature up right near a terahertz. And when you show the others, it doesn't quite look consistent with the dimer model you showed. I'm curious about
This
that
one?
feature. Yes.
Well, this is a problem of inaccuracy of water monomer line. Of course, it should be smooth figure. Well, it's understandable.
Well, if you advance further, there you go. I know, and now you have your dimer, the model dimer. There you go. So you can see it sort of matches that feature, but it looks like almost a registration or some other issue. But it's a fascinating feature up there. I'm kind of curious if you had any other explanations.
Are you talking about this feature or what feature?
Yeah. Yes.
Well, this feature appears as some problem with the pressure broadening of water line at this frequency in Hydra. So minor error in line intensity and line broadening can produce such features in continuum. And I'm absolutely sure that the continuum spectrum is smooth here. And this gap in the spectrum, they correspond to vicinity of the line center of the very strong water lines.
Yeah, it's really very interesting again to see that the dimer effect has really spectral behavior. It has
Yes.
line behavior rather than in any way a continuum that we've been thinking of it as.
Yes, this is a spectral function, and recently we have studied the spectrum of CO2. You know, it does not have resonance lines in this range because of absence of dipole moment. But the spectral function is very, very similar. And if you like, I can show you. I have this picture in this presentation. Would you like to see it?
No objections here.
Okay, let's go. Well, this shows.
I think Professor Tretyakov, though, I'm going to have to formally end our session because other people will be moving to other sessions. But
Yes,
I would
okay.
certainly love to continue on. So I'm going to do the following. We have one more question from our URSI chair, Mike Meeker.
Professor Tretyakov, it's not so much a question, but as a comment. I want to thank you on behalf of USNC-URSI. I'm the current chair of the organization. I really appreciate your time, especially knowing what time it is in your time zone, that you would share your excellent work. I really appreciate that time, and I think it's outstanding presentation. Thank you very much.
Yes, thank you very much.
And I'd like to also thank you very much. So this formally ends our session. I don't know if Professor Tretyakov will be able to stay up for very much longer, but I know I could talk about this for.
Yes, if someone would like to talk to me, I can stay as long as you wish.
I'm curious, when you have the CO2 argon coefficients, I believe if I'm looking at this right, this is CO2 argon broadening. Have you scaled out frequency, or is it with frequency in it?
Well, this is a wave number below and gigahertz above.
Yes, okay, and so no
the
division. But no division by frequency squared.
Well, it's already divided by frequency squared.
Ah, okay, yeah, it's got a similar behavior in that range.
Yes.
Would
yes,
this
this peak at low frequencies and this shoulder, and it's the same thing. You see, this is a rotational envelope of rotational spectrum. It doesn't have dipole moment, but somehow just it keeps the envelope of rotational lines of CO2. And if it would be a dipole moment, then you will have lines like usual spectrum.
Would the suggestion be that CO2 and argon are forming a dimer of sorts?
Yes, of course.
That's interesting.
Yes, and well, there is no sign here, but these solid lines, they correspond to the total contribution of stable dimers and metastable dimers and free pairs. So 3 possible pair states. And dashed lines are without stable dimers. So this big difference is due to stable dimers. So
this is very
stable
interesting.
dimers really contribute to this spectrum. And this is very general physics. And for every molecular pair, you have to take into account.
Yeah, this is very interesting. Now, I think we are going to have to move on to our next session in this room. So we will have to close. But again, I want to express my deepest appreciation for your presentation to our audience here. And I really appreciate your work. Thank you so much, Professor Tretyakov.
Thank you, Al. Thank you.